Okay. Good morning to all. Mm. Uh, Last class, we have discussed the two-dimensional transformation. Uh, the objective of the 2D transformation is we have to change its location, its position of an image. Not only position, we can also change its size. We can resizing it by enlarging it or squeezing it. Besides that, we can also rotate it uh, to specify angle either clockwise or anti-clockwise. Uh, Also, we can get an image by reflection and mirror image of an image with respect to x-axis, y-axis, or any other line. Uh, uh, so the main transformation technique is translation, which is associated with the change in position; rotation, which is associated with the rotating in body of an image or an object; scaling, which is associated with the resizing. Besides that, there are two other transformation: is reflection, which is to get an image of mirror image, to get a mirror image of a reflection with respect to any line or respect to x-axis or y-axis. Shearing, the shearing here is the change in the shape, the change of a shape of the object. So we have already know that these are the uh, geometric transformation techniques, and you see it is written that changing the object of position, translation; orientation, if you rotate one side, that is rotation; and if you change the size, it is called scaling. So in previous class we have discussed that is if a point is P, we can change the position of that point to P dash by using translation. So translation only help us when we want to change the location, the position of an object. So here we can able to, you see P is here and P dash is a new point. So we can able to only change the position. Otherwise, no other thing are the size, shape, or rotation is not there. Only change to its position. Uh, Here we are able to only change the position of a point. Similarly, we can also translate a line. How we will discuss. Please recall that is a line has two endpoints. A line has two endpoints. So we that is 2 points. So we have to translate each point separately. Suppose P is a one endpoint, Q is another endpoint. We have to translate P first and then Q. P dash, it becomes related P dash and Q dash. So join P dash Q dash. So it has become the new line. That is the new that line should be new position. So now we are able to change the position of a line. Similarly, triangle. Triangle also, you know that triangle has three endpoints, 3 points. So we have to apply the translation technique in all these 3 points. After translating, we have to region that point. Similarly, in case of polygon also, if a polygon contains some multiple lines, suppose there's a hexagon related 6 points. So we have to apply the translate technique to all these 6 points, and after translating a new points, we have to region that points, and we get a new polygon, same polygon but in new position. So in this way, we can change the uh, position of an image by using translation. Uh, Besides that, you know that rotation we have already discussed. I am just recalling the rotation axis. You see, we need this thing for rotation. Rotation axis, rotation angle, and rotation point, which is known as x or y r, or sometimes suppose it may be an origin. So you see here, if we rotate theta as positive, that is it is anti-clockwise or counterclockwise. If theta is negative, it is clockwise. And this is the translation matrix. Please recall that is r equal to cos theta minus sin theta and sin theta and cos theta. So if you see, this is first is xy. We have to rotate this line about theta with respect to origin. The pivot point is origin. So you see the image uh, 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 below. So xy you will get x dash y dash by rotating the angle theta. And it is not required. And this is the scaling. You see, scaling is used to alter the size of the object. If you want to change the object, so suppose x y is the position and x become y dash equal to x into sx. But you recall the translation, it is x plus tx, y plus ty, y dash equal to y plus ty. So in translation, it was x plus tx and y plus ty. But in case of scaling, we have to multiply the scaling factor sx and xy with corresponding x axis and y axis value. So x dash become x into sx and y dash become y dash sy. And if we want to represent in matrix form, so x dash y dash matrix, it is a column matrix, and sx 0 and 0 xy into xy. That is, if you multiply the two matrix in the right hand side, you will get x dash equal to sx plus y. Sorry, xs plus x. Xs into x plus 0 into y. That is xx into x. So x dash become x into sx. Similarly, if we multiply for y dash, so y dash equal to 0 into x 0 plus y into sy. That means y dash equal to y into sy. So in matrix form, you can write p dash equal to s into p, where p dash equal to s dash y dash, s equal to the middle, uh, that is the scaling factor matrix, that is sx 0 0 sy dot xy. So we know that if the value ss is less than 0, it is reduces. If value greater than 1, it is enlarged. If scaling factor is 1, then the object stayed unchanged. So if xs and sy both are same, so there is a uniform scaling. That is, you scale here same x-axis as well as in the y-axis. That is why it is uniform scaling. And another important thing is, if scaling factor less than 1, the object moves closer to origin. That is, not only the object size decreases, but also the object comes closer to the origin. Similarly, if it is greater than 1, if the scaling factor sx or xy is greater than 1, not only the object enlarge, the object size increases, but also the object moves away from the origin. You see here, the xy, after scaling, the size decreases. And you see here also another point you have to mark here, that is the size diminishes, the size decreases, because here the scaling factor value must be less than 1, so it decreases. And another thing you may point that, that is it come closer to the origin. After the size decreases, the objects comes closer to the origin. then matrix representation and homogeneous coordinate. So many graphics application or in many representation, we need a homogeneous coordinate. Homogeneous coordinate in the sense, actually we are learning here 2D transformation, 2D, two dimensional. So many application is associated with the 3D, that is your length, breadth, and height. So, but we are here only 2D. So that is why we have to represent this 2D to a 3D matrix. You see here in previous one, here is a the scaling factor. You see it is a 2D matrix. You see S dash Y dash column matrix is equal to XS0. It is also a two-dimensional matrix. XY also a two-dimensional matrix. So some graphic representation is unable to represent it. So we need to represent it using a homogeneous coordinate system. It is help us to make animation, to apply some other design or picture construction applications. So that is why we have to need represent this matrix in a homogeneous coordinate. And another benefit we will get if we represent it homogeneous coordinate, that the sequential transformation can be efficiently processed. Sequential transformation, that is, we want to apply translation, then rotation, then scaling. Keep fast scaling, then translation, then rotation. So this is your sequence of transformation. So if we represent an image in homogeneous coordinate, it will be uh, easily done. So this is the formula: P dash equal to M1 into P M2, and you come directly to the uh, uh, matrix representation. You see here, this is the translation matrix. You see, now I am able to represent the 2D translation matrix into 3D one. The result is same. That is, if you write, if you see, if you multiply the two matrices in the right hand side, you will get S dash equal to x plus tx, y dash equal to y plus ty, and 1 equal to 1. You will get the same output, but here we are able to represent this matrix in a 3D form, in a homogeneous coordinate. So we can write P dash equal to T, that is the translation matrix, tx ty dot P. P is the original location, P dash is the new location. So T is the translation matrix, applied to P, we will get P dash. Similarly, the rotation matrix, you see, I have only added a extra row and extra column, 0 0 1 0 0 1. Otherwise, it is same in case of rotation matrix. You see here the scaling matrix, that is the inhomogeneous coordinate. The same matrix here. If you compare this scaling matrix with previous one, which I've already discussed, you see. 1 minute. Come to this slide. You see. You see, a dash y dash equal to xs0 0 y xy. The same matrix is there, but in a 3 cross 3 matrix. I have only added 1 0 0 1 0 0 1 1 extra column, extra row, and in column matrix in 1. You only, if you will be clear if you compare this matrix with the translation matrix in homogeneous coordinate. You see this one. Same thing is there, that is x dash, y dash, SS00. So I am adding only a new column 001 and new row 001. So here P dash equal to S into P, same thing. But I am it is represented in a homogeneous coordinate. Inverse transmission. It is, as the name suggests, inverse. It is opposite to translation. It is opposite to transformation. That is, suppose we have added translation. My original position change. After that, I want to come back to the original place. Uh, 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 Suppose, let me discuss again. That is, what is inverse transmission? Suppose translation is a transformation, we know. Suppose we apply translation to a point or to a line or to a polygon, whatever may be. Suppose after translation, the object change its position, and now I want to come back to my original position. And why I mistakenly came, or suppose my work is not done, or my work is completely done. Again, I want to come back to the original position. You apply the inverse transformation. So that is why you see here it is written as T inverse. This is the translation matrix. I have added that. Now it is subtracted. That is 1 0 minus Tx. Minus Tx. That is, if we have added in a translation, we have to subtract here. If you subtract in translation, we have to add here. So 1 0 minus Tx, 0 1 minus Ty, and 0 0 1. Similarly, you see the sign changes. Initially it was cos theta minus sin theta, 0 sin theta cos theta 0, and here the minus sign comes to the second row sin theta in second row. So that is, if we rotate an object to a specified angle, and after rotating I came to the original position or original position of the object, we have to use 2D inverse rotation. Similarly, if theta is negative, it is clockwise. Only sine function is affected. Therefore, we can say R inverse equal to RT. So similarly, in place of inverse scaling matrix, we have to divide here. You see 1 by Sx. In original scaling matrix, we have to Sx 0 0 0 Sy 0, but here S inverse equal to 1 by Ss. That is, we have to divide, or we have to multiply 1 by Sx to S to get the original size. That is, suppose the size of an object changes after scaling, and then after that we did not want to change their size, or you want to retain the original size, but you have already applied the scaling factor. Now we want to retain the original size, so we have to use the inverse scaling inverse scaling matrix to get your object in original size. So far we have discussed translation, rotation, and scaling. Translation is used to change the position, rotation is used to rotate an object, and scaling is used to resizing an object. We have also known that we have also two important translation: shearing and reflection. We'll discuss about that. But there are five main translation technique. Out of five, we have already discussed three. Now, 2D composite transformation. That is, we can apply sequence of transformation as a composite transformation matrix by calculating the product of the individual transformation. That is, we can apply at a time the composite transformation. That is, we can apply translation and rotation simultaneously to our object. Okay, that is called your composite transformation. That is, you see the P dash equal to M2 M1 into P. M2 is the first transformation, M1 is the second transformation. So the last one is M dot P, that is M1 into M2 equal to M, let it M, so dot P. So M is here the composite transformation. It may be the rotation followed by scaling, or maybe translation followed by rotation, whatever may be. That is, here we have to simultaneously apply more than one transformation technique, M1, M2. Let us see. Composite 2D translation. If two successive translations are applied to a point P, then the final translation location P dash is calculated as. Suppose we have to apply two translation, T1 and also T2. So here you see here P dash equal to T T2 x2 y2 dot T T x1 y1 dot P, and that means the final is, you see, one, we know that 10 T2x 01 T2y 001 dot this, and we will get at final 10 T1s plus T2x 01 T1y plus T2y then 001. Okay. So we have to apply the final matrix to the P and get, that is P dash. We need not to translate twice. So first you multiply M1 and M2, and that is suppose M, and then multiply M into P to get P dash. So you see, this is the composite transformation we have added, we have applied. Similarly, you have to add the composite 2D rotation. That is, you have to rotate 30 degree. Then suppose 30 degree to suppose clockwise. Then suppose 50 degree to anti-clockwise. Otherwise clockwise. Whatever maybe. That is, you have to apply both rotation at a time. You see, then P dash equal to R plus theta 1 plus theta 2 into P. So the final, you see, you have to multiply that two matrices. First, for theta 1 is written, theta 2 is written, and then theta 1 is written, M2 into M1, then multiplied it. You will get cos theta 1 plus theta 2 minus sin theta 1 plus theta 2, 0, sin theta 1 plus theta 2, cos theta 1 plus theta 2 plus 0, 0, 0, 1, 0, 0, 1. This is for homogeneous coordinate system. It is same as cos theta minus sin theta, cos theta. We have to here only I have only taken theta 1 plus theta 2 in place of theta, because it is a composite transformation. That is, first we have to rotate theta 1 degree, then theta 2 degree. Okay, so we have to finally apply this single matrix M to P. We need not to rotate both one by one. You have to first multiply M1, M2, it will become M, and then multiply the M with P to get P dash. Similarly, the same thing is applied to scaling. The same is applied to scaling. You see, suppose I first want to scale x1 and x1 and sy1 is the scaling factor, and then we have to again apply scaling factor x2 and sy2. So instead of applying one by one, first multiply these two matrix. You see, I am multiplying this, and the final matrix is s1s dot s2x 0 0 0 x1y s2y and 0 0 1, and we apply direct matrix to P. So two composite transformation, it is clear that if there are two transformation m1 and m2, you first multiply m2 m1 and then multiply the resonant matrix with P to get the new matrix P dash. That is, if two conjugative translation is there, you multiply first translation matrix to the second translation matrix. Similarly, in place of rotation also, and also scaling also. So this is your 2D composite transformation. Successive translation are additive. Successive scaling also multiplicative. That is, if we triple the size of the object twice, so no doubt the final size will be 9 times. 3 into 3, 9 times. So it is a multiplicative. Similarly, if we add the additive, it 3 times, 2 times, it will be 5 times of the translation. So your general pivot point rotation. So far, we rotated an object with respect to origin. With respect to origin, theta degree, either clockwise or anti-clockwise, but the respect to origin. Okay. Now we can rotate any object towards with respect to any other point, not other than the origin. If it is respect to origin, it is easy. It is easy, you can rotate. But now I want to rotate an object with respect to any other point other than origin. Other than origin. So that is called the pivot point. That point is known as the pivot point. So far, the pivot point was the origin. It is easy. If you go back to the rotation side, you see we have rotated that object. Where is that? You see. You see these slides. There's a point xy. There's a point xy. The original point is there. Now I rotate that line, that point to x dash y dash through a angle theta anticlockwise with respect to origin. You see the angle, there is a theta angle with the respect to origin. So this rotation is done with respect to origin. So the pivot point is here, the origin. But now we are going to discuss, we want to rotate an object with respect to any other pivot point. any other pivot point. It is not the origin, other than the origin. Let us see how. Here, you see, general pivot point rotation. General pivot point, not the origin. So if it is origin, it is easy for us. Let us see. We have to follow these 3 steps. Translate the object so that the pivot point is moved to the coordinate origin. So we have to rotate that at origin about the pivot point. So first we have to translate that pivot point to the origin. So now the pivot point is the origin. So now it is easy for rotation, which is done in second step. You see, rotate the object about the origin. So once it is rotated, then you make inverse translation. Translate the object so that the pivot point is returned to the original position. Inverse transformation. That is inverse translation. That is step 1 and step 3 are opposite to each other. You first take the pivot point to the origin. So once the pivot point to origin, it is easy for us because we know that how to rotate the object with respect to origin. In second step, we have done that. So after the rotation is take place, now we have to apply the inverse translation. That is to get our pivot point to its original position. Bas, done. Okay, let us see. This picture make you clear about the pivot point rotation. You see, there is a triangle, blue color triangle, and you see there is a point, white point inside it. I want to rotate this object with respect to that point, not the origin. That point. That point should remain fixed, but we have to rotate the object either clockwise or anti-clockwise. Suppose I want to in anti-clockwise 90 degree. Let. Okay. So not to the origin. You see, first one is the original object, and you see the pivot point. The pivot point is there. It is a white dot you see on that inside the triangle. I want to rotate that. That is the pivot point means it will not change. The other point of that object will be changed. The other points, because you see there are a lot of points inside that triangle. So the pivot means that is that point should remain fixed. It will be not changed at any circumstances. The other point will be changed. So that is why I call this pivot point. So I now want to change the rotate the object with respect to that point. Means that point should be remain fixed in the object. Okay. So if we apply direct translation rotation matrix, it will be wrong. Why? That is, it will be with respect to origin and all the size will change. So we have to follow these 3 steps we have discussed. First, we have to translate, we have to change the position of the pivot point to the origin. How? Translation. We know that translation is used to change the location. So we have to first apply the the translation to change the position of the pivot point to the origin. You see the second one. Now the pivot point is changed to the origin. It comes to the origin using translation. So once it is translated, now you rotate it by using with respect to origin. It is easy for us. We have a translation matrix formula. How to translate, you know. So now you rotate. You see, suppose it is rotated 90 degree anti-clockwise. Now you rotated. You see the third image. Third image is rotated. But this is not our desired output. This is not desired output because we want to change the object with respect to the pivot point. So, but the pivot point is changed. Pivot point means it should be fixed after rotation. So, we have to apply here the inverse translation. The inverse translation. As we discussed in the previous slide, inverse translation, we take that point to its original location. So that is, we have to make the inverse translation, that is opposite to step 1. In step 1, we make the translation from the pivot point to the origin. Now origin to the location of the original pivot point. You see. Now my work is done successfully. I have rotated with respect to that pivot point. That is, the pivot point is fixed. It is same as there as it is original position. You see, you can compare the first one and the fourth one. The pivot point is fixed, but the object is rotated with desired angle. Suppose 90 degree here. It is. So this is general pivot point rotation. General pivot point rotation. So these 3 steps is successfully applied. First translation, then rotation, and then again inverse translation. You see, I represent those techniques using a matrix representation. First is the translation 1 0 XR 0 1 YR 0 0 1. Then rotation cos theta minus sin theta 0. You know that this is the rotation matrix, rotation transformation matrix. First one the translation matrix, and last one you see this is inverse translation matrix. Inverse translation minus XR and minus YR is there. So as you know, this is a composite transformation. First translation, then rotation, then again translation. So we have to multiply these three. We have to multiply these three and get M. Now you apply M into P, which will become the new P dash. Similarly, we can make general fixed point scaling. General fixed point scaling or general pivot point scaling. So far, we scale an object with respect to origin. With respect to origin. So if we scale a point or scale a line, it is easy with respect to origin. Now we have to scale an object with respect to any other point, not origin. Other than origin, we have to apply the scaling factor to the object. Similarly, same thing is there. Translate the object so that that pivot point or a fixed point coincides with the coordinate origin. Once it is come to the origin, it is easy for us Then scale the object, because now you are in origin. With respect to origin, you have the knowledge how to scale the object with the origin. We have the scaling factors. You apply the scaling matrix, scaling transformation matrix to get the new size. So we don't have any problem in step 2. So once the scaling is done, this is not our desired output. हम क्या चाहिए ना, translate to the object so that the pivot point is returned to the original position. So again you have to return, you have to again the translation technique again. You see here. Now this is a, you see the first picture, it is a triangle which is given in blue color. You see bluish color there, and we have to change the size. We have to change the size of the object. Suppose it is isosceles triangles, we have to change its an equilateral triangle. I think you see it is looks like a equilateral triangle. That is, I want to change the size. Finally, that is my aim is to want to change the size, but with not respect to the origin, with respect to that fixed point, pivot point, x r y r. That is, I am telling fixed point means this side will never change. Sorry, this point, the position of this point will never change. The other point may change, but this point should be there at the fixed position. If you compare the first image and the fourth image, you see the XR wire point, the white dot is there. It remains in the same position. If you compare the original positions or the resultant object, first one and fourth one. So we have to make the same technique here. That's why we have to translate that XR wire to origin. So you see in the second picture, the work is done. That is now you are in origin. We don't have any problem to resize the object. Why? Because we know we have the scaling factor, we have the transformation matrix to change the object. So you apply here that matrix, and after that you will get a new image after resizing. Image number 3, you see picture number 3, first, second, third. You see third one. Now it is changed. The size is changed because I have applied the scaling factor. As you know, scaling changes the size, so the size changes. The size of the first one now it changes, but yeah, output नहीं है, final output नहीं है. This is in the pivot point is in origin, but we have to translate that object to its original position. That is using inverse translation. That is the step 2 opposite of step 2 opposite of step 2. So again you see that pivot point comes to its original position. So this is a fixed point scaling. Why it is called fixed point scaling or pivot point scaling? Because that point which are taken as fixed point or pivot point, it should remain in the same position as its original position. the other point of that image may change, but that point should be remain fixed. That is why it is called fixed point scaling. Okay, we again see the pivot point x r y r in the first original position and the last one, the resultant. It remains exactly the same position. The other point in the image will change. The other point will change because it is resizing, so other point may change, the location of other point change, but that point through which we have taken the make a scaling, so that point is called a fixed point scaling or pivot point scaling. So we can represent it using matrix. You see, first one is the translation, second one the scaling, third one is the inverse translation, minus s. You see, minus xf minus yf. So if we multiply this thing, you will get the final matrix. If you multiply these three, and you can apply it to the p to get that p dash. So this is also a composite transformation. First one the matrix, then scaling, then again translation, scaling, again translation, inverse translation, but it is translation. So this is the matrix form of the general fixed point scaling. So in this way, we can scale or rotate an object with respect to any other point, any other pivot point other than origin. We have to translate that to the origin. Now it will become easy, then again translate back. Composite transformation, we know that the scaling parameter were along x-axis and y-axis direction, sx and yi. So when we make scaling, either with respect to x-axis and y-axis, that the scaling factor sx and sy. So x-axis is the scaling factor about x-axis, and sy is the scaling factor of y-axis. We can also take the above parameter, you see, scaling factor xs and xy with other direction. Okay, so any arbitrary direction, not about x-axis and y-axis. Okay, so let us see how. Scaling parameter S1 and S2 along orthogonal direction defined by the angular displacement theta. So we have to make another theta, you see. Then we can coincide this with the origin. You see what to do. Rotate so that the direction coincide with the x and y axis. You see here. So now we have to rotate. Suppose we have to change the size after the scaling factor with the line S1 and you see S1, S2. It is not the x-axis, y-axis, x-axis, y-axis, and other things. So you see here, the S1 makes an angle theta with the axis x. So if we rotate S1 anticlockwise, you see, if we rotate S1 anticlockwise theta, so that is S1 and S2 now S1 is the coincide with x. Similarly, you rotate S2 so that it will coincide with y-axis. So now S1 and S2 coincide with x-axis and y-axis. So now it is easy to scale because we know that how to scale with the x-axis and y-axis. Apply the factor xs and sy. The same procedure written as you see. Rotate so that direction coincide with x and y axis. Apply scaling transformation, then rotate back again. Okay. So rotate thing now it will become that two direction become the x axis and the y axis respectively. One it is coincided with x and y axis. It is easy for us. We know the procedure how to apply rotation. So apply scaling information S1, S2, then rotate back. This is the matrix for first is rotation. You see, first r theta, that is M3, M2, M1. We have to multiply first M3, then M2, then M1. So M1 means first one you see r theta, then scaling S1, S2, and the final is r inverse theta. That is M3, M2, M1. And finally, if we multiply the three matrix, we will get this. This is a composite matrix. You see, matrix multiplication is associativity. So M3 into M2 into M1. We have multiplied first M3, M2 into M1 or M3, M2 because we know that the matrix multiplicative are associative. A composite matrix can be created by multiplicating left to right or right to left. So matrix multiplication is not commutative. So M2, M1 may not give you M1, M2. It may not be same because matrix multiplication is not commutative, but it is associative. Sometimes it may be confuse you if the two successive rotation or two successive translation, two successive scaling are commutative or not. Commutative means suppose there are two successive translation T1 and T2. You first make T1, then T2. You get a new position. Or you now inverse the order. You first make T2, then T1. You will also get another position. Is they same? Are the both are same? Let us see. You see, reversing the order. In which sequence of transformation is performed may affect the transform position in an object. You see, in first picture, an object is first translated in the x direction and then rotated anticlockwise through angle 45 degree. First rotated here and then rotated. You get the final position anticlockwise 45 degree. Now I reverse the order. I reverse the order. First you rotate it 45 degree anticlockwise, then translated the x direction. You see the final position. So it is clear that is these are not commutative. Okay. If we translated first and then rotated, you see the final position in blue color. In second one, you see, if we rotated first, then translated, simply change the reverse the order. You will get a new position. So the output of the first one is not the same as the second one. Please write your name and registration number in the board for attendance. Those who have not written, please write. So far we have discussed three major transformation techniques: translate, translation, scaling, and rotation, and composite transformation, and also rotation and scaling with respect to any other pivot point other than the origin. And now the reversing the order, if you change the order of the transformation, we may get the different output. So the transformation, composite transformation may not unique. Then come to the fourth one. You see, uh, other to the transformation, first on the reflection. The fourth one, after translation, rotation, and scaling, this was the fourth one, uh, reflection. Transformation that produce a mirror image of an object is called the reflection. So you see, this is the original object, which is done in a dotted line, dotted blue color line. You see, and after the reflection position, we will get 1 dash, 2 dash, 3 dash. That means if we keep a mirror over x-axis, on the x-axis, if we keep a mirror on the x-axis, we will get exactly an image of that object, which is dependent by 1 dash, 2 dash, 3 dash. And this is the reflected image about x-axis, because the mirror is placed on x-axis. So it is same as when we stand in front of a mirror, we see our image, and this is the mirror image. You can tell the reflection is nothing but this is a mirror image, and transformation that produce a mirror image of an object is known as reflection. So if we place a mirror here on x-axis, we will get exactly the same image that is shown in the picture. So this is I can tell that is the reflected image of the object when we reflect with respect to x-axis. Similarly, you see here the reflection matrix. This is important. You see, the image is generated relatively to an axis of reflection by rotating the object 180 degree about the reflection axis. So reflection about the line y is equal to 0. You know that in the x-axis, all the point of y is 0. So that is why you see the reflection matrix about x-axis is 1 0 0 0 minus 1 0 and 0 0 y, means y position is changed minus 1. So this is the reflection matrix. You if you represent it in general coordinate other than the homogeneous, you will get 1 0 0 minus 1, because 0 0 1 0 0 1 the row and column is added for homogeneous coordinate only. If you remove them, you will get only 1 0 0 1. Sorry, 1 0 0 minus 1. 1 0 0 minus 1 in present 2D matrix. So uh, so about x-axis, the y-axis becomes 0, and this is the reflection matrix about x-axis. Similarly, we can reflect an object with respect to y-axis where x equal to 0. We know that all the points on y-axis, the x value is 0. So this is the reflection about line. x equal to 0 or about the y axis. So you see the original position, and if you place a mirror on y axis, you will get exactly image as represented in blue color in the, you see, 1 dash 2 dash 3 dash depended by the point 1 dash 2 dash 3 dash, the original position 1 2 3. You see the reflection matrix minus 1 0 0 1 minus 1 in the x axis, so x position is changed only. So in previous one it is a minus 1 in the y second row, but here is the minus sign in the first row for x. So this is the reflection matrix about y axis, and the previous was about x axis. Similarly, uh, we can reflect an object with respect to origin. That means the combination of x axis and y axis. You can tell the combination of both. That is, you have to first rotate it in the x axis and then y axis, or first y axis then x axis. So it will be, you can tell that is the reflection about the origin, and it will be clear if you see the matrix. In place of x axis, it will become minus 1 in second row, second row 1, and uh, about y axis the minus sign was in 1 in the first row. Now we combine both. So you see there's a minus 1 in first row, also then a minus 1 in 1 in second row. So this is the reflection about the origin, with about the origin. So origin in the sense that is we have to reflect with respect to both the eyes, both the axes. First is x axis, then y axis. Now you see reflection about line y equal to x, that is 1 1.22 33 44 55 66, y equal to x. You see origin the 0 0, then the line passes through the point 1 1 2 2 3 3 4 4 5 5 and 6 6 7 7 and so on. And this line makes an angle, you see, that is the exactly divides the first quadrant, exactly two equal parts. And now I have to reflect a light, represent the object not with respect to x axis, neither x axis nor y axis, but we have to reflect the line with another line, another pivot line, another line other than the x axis and y axis or origin. That line is y equal to x. That means the line passes to a point 0 0, y equal to x means 0 0 1 1 2 2 3 3 4 4 like that. So you see the matrix 0 1 0, there is no negative signs because they are the that position, the original position remain in the same quadrant, the same quadrant. So there will be no negative sign. Similarly, if we represent y equal to minus x, you see y equal to minus x, that is the opposite direction, the same line in the opposite direction, y equal to minus x, that is 0 0, minus 1 1, minus 2 2, minus 3 3, like that. That line, you see, the line passes through minus 1 1, minus 2 2, minus 3 3, minus 4 4, minus 5, plus 5. You see. So this is the reflected object. 1 2 3, the original position. If we repeat that, you see 1 dash 2 dash 3 dash is the, so we have to here minus 1 in the, and minus 1 in the middle. You see the first row, the second one, and the second row and first one will become minus sign. So this is the reflection of line y is equal to minus x with respect to not x axis and y axis, but a line is y is equal to minus x. So we have to rotate also a an object with respect to these lines. So far we have discussed about the reflection with about x axis, with about y axis, with about origin, with respect to y is equal to x or y is equal to minus x. And now come to the last one. The last transformation, number 5, shearing. Shear. Transformation that distorts the shape of an object, not the size. You more clear about the shape and size. Transformation is a destruction of the shape of an object so that the transformed shape appears as the object was composed of internal layers that had been caused to slide over each other. That means shearing basically is used to change the distort the shape of an object. Suppose there is a square, you make it a rectangle, but the area will be same. The area will remain same. So this is just change in shape, so that the transformed shape appears as the object was composed of internal layer that had been caused to slide over each other. You will be more clear. You see the image. You see there is a rectangle. There is a square in the first image. So after shearing, we will get a parallelogram. It looks like a parallelogram. Okay. So this is called shearing. Suppose you have a wire. You have a wire. You make it a circle. Now, by taking that wire, you make a rectangle. By using that wire, using a square. By using that wire, suppose you made a parallelogram. That is, you only change the shape. This is called shearing. That is, you see, we have to change the shear and x direction with relative to y axis. So as x direction, you see, you remember it is in scaling we have to make more both the direction ss and sy. But here you see, we have only changed the x coordinate, but y dash remains same. Y axis remain, y coordinate remains same. So this is just shearing with x direction, and y direction the object remains same. That is why 1 SSS and x dash equal to x plus SSS into y. That means x is changed with respect to y. And y dash will equal to y means y value does not change. Similarly, and y direction shear related to the x axis is 1 0 0. SSX y 0 0 0 1. Let us see. And this is your X direction share related to other reference lines if the line is not the x axis and y axis. You see here, this is a rectangle size, and after sharing, we will get a parallelogram, a square chain to parallelogram having a y reference equal to -1. We have taken the there, and s is equal to 0.5. That is become 1 become half, so that it is reflected there. Similarly, if y direction share is SSY, 1 SSY, that is x dash will not change, x will not change, y will only change. You see here, I am taking the x reference, means y, that is the object will slide to y axis. So here also the a square is a shape to separate to parallelogram. So this is shearing, which you want to change the shape. We have discussed all these uh, transformation technique, translation, which you want to change the size, the rotation, scaling, shearing, and reflection. So these are all translation techniques used in 2D rigid body transformation, and this is all about your transformation. Then let us discuss a new topic, computer vision. Then let us start a new topic, computer vision. Let us see what is the computer vision is. Computer vision is a branch of AI, artificial intelligence, that enables computer to interpret and extract information, exact information, extract information from image and video, similar to human perception. That is when we human view an image, we extract some information from it. Suppose we see an image, we started it is face, it is the face, it is the image. No, suppose we see an elephant. Suppose we see an image of an elephant. We see the elephant's face, elephant's leg, elephant's tail, elephant's tongue, all the things. Because we have eyes, we know that this is an elephant, and this is the part of the body part of the elephants. When we see a flower, we see the flower is how beautiful it is, and it is smells well, it looks like good. So its color is red, so we see that. That is, we extract some information by viewing an image. Yeah, suppose satellite image, suppose currently from the satellite we show that where is the to where we have to target. Suppose in the war by viewing the satellite image. So this image viewing the image or computer vision is an important topics. Is an important topics. That is how the machine. What is the machine vision? Is similar to human perception. It involves the developing algorithm to process visual data and derive meaningful insights. So we have some specific algorithm, specific procedures to get the visual to meaningful insights or meaningful information by viewing the data. So like a human, computer also get or extract information from the object, from the uh, that picture. That is called the computer vision. As the name suggests, computer vision. Well, how can computer view it? How does the information extracted by the computer from that image? So this is called the computer vision. So let us see why. Why computer vision? Why to learn the computer vision? These are the high demand in the job market. But you see that essential for career in AI, machine learning, and that these are the challenging career nowadays. AI, machine learning, and data science across industry like healthcare, automotive, and robotic, telecom also. So these are robotic, automotive, and healthcare. In these sectors, uh, the computer vision plays a vital role. Revo- Revolutionizing industry powers advancement in self-driving cars. Self-driving car, that is you sometimes view in the TV that the car is moving without a driver. Medical diagnostics, agriculture, and manufacturing by automating visual text. That is human does not have any role here. By viewing the machine will be take the necessary decision. Solving real world problem, enhance public safety, improves medical imaging, and optimizes industrial process. So this is also a factor how to learn computer vision. Have you ever wondered how a machine can see and understand the world around them much like a human do? Okay, so like a human do or better than a human do, how machine can view, see, understand world and understand the world around them. So when we are view an image or when we learn something around our environment by viewing it. This environment is not good. The garbage are there, all there, and this is not suitable for our health. But viewing it. So how does the machine know? How does the machine extract the information? This is the magic of computer vision. That is, this is a branch of AI that enables computer to interpret, and analyze the digital image, video, and other visual inputs. The computer will be analyzed like a human or better than a human. That is, the computer interpret it, analyze the digital image, video, and other visual inputs. For self-driving car to healthcare diagnostic, already discussed. Computer vision in revolting industry by allowing machine to recognize object, track movement, and even make decision based upon what they see. The other application are oil and natural gas. This is also an application to the oil and natural gas companies produce millions of barrels of oils, you know that, in cubic feet or gas every day. But for this to happen, first the geologists have to find a feasible location from where oil and gas to be extracted. To find this location, they have to analyze 1,000 of different location using image taken to the spot, because they have no times, or it is very difficult to visit all the location physically. Okay. To find a better location for oil or natural gas, that the geologist need not to visit physically all the places of a country where it is better it is suitable for oil and natural gas. So they have to analyze thousand of different location using image taken to the spot. The image will be taken. Then they have to analyze if which place is better or not. Suppose a geologist had to analyze each image manually. How long would it take? So suppose you take what I've discussed. If the geologist had to analyze all the image manually, how long would it take to find the location? Suppose the image are there, they have to view them manually. So a long time will be taken. So maybe months or even a year due to the introduction of computer here. But due to introduction of computer vision, the period is analyzed can be brought down a few days or even a few hours. But by using the computer vision technique, this work can be done within a few days or a few hours. So you just imagine how the computer visions help us in these matters. Hiring process also this is used. In HR world, computer vision is changing how candidates get hired in the interview process. By using computer vision, machine learning, and data science, they are able to quantify soft skill and conduct early candidate assessment to help large companies shortlist the candidates. Also, video surveillance. This is also the video tagging used to tag video with keywords based upon the object that appears in each scene. So imagine being that security company who asking to look for a suspect in a blue van amongst hours and hours of footage. It has to feed the video to the algorithm. With computer vision, the object recognition searching through video has become a thing of the past. So suppose a security region, suppose there is a spurious car is moving, suppose its color is red, so all the red color would be analyzed or recognized by the computer vision. With computer vision, the object recognition, we'll discuss how the object is recognized, and object recognition searching through videos has become a thing of the past. It is also used in construction. For example, the electric tower or building which requires some degree of maintenance to check the degree of the rust in other structural defect. Suppose there is a construction, we take the example of a uh, electric tower or a building. So manually climbing up the builder or tower to look at every inch and corner would be extremely time consuming. If you manually check, a person will be climb, a person will climbing and check which part is damaged, which part is rusted. So it is take a long time. Uh, so it may be time consuming, may be costly, or may be dangerous, because climbing a tower, climbing a tower or building, it may be risky, it may be dangerous, may and costly, also time consuming. But imagine if a person on the ground took high resolution image from the different angles, then the computer vision specialist could create a custom classifier and use it to detect the flows of the amount of rust or cracks present. So high resolution, instead of this, we take high resolution pictures, and then a computer vision specialist will be check that the which part is damaged, which part is needs maintenance, which parts needs repair, and the cracks or rust present in the tower, iron tower. So it will be easily determined. Healthcare. From the past few years, the healthcare industry has adopted many next generation technology, including artificial intelligence and machine learning concept. One of them is computer vision, which helps determine to diagnose disease in human and any living creatures. So it is also used in healthcare. The agricultural farm have started using the computer also use, military also use, and industry automotive, and these are the automated leaf reading we'll discuss. So we'll discuss from this the next class. So uh, I will send the PPT of transformation slides and these slides. So you please you go through it. Please write your name and registration number. Please wait a while. I will take the snapshot.
Okay, sir.
Okay, 1 minute. So please write your name and registration number. Those who have not written. So now you can leave. Thank you. Thank you to all.
Thank you, sir.
Thank you.
Thank you, sir.